Alrighty, hello everyone. Today is the last lecture of the Gridspace IAP 2025 from Bytes to Beats. As you can see, today we're at a different venue. Anthony was talking about having this lecture series have a cinematic finish. So today we are filming live from the Union Theater in Los Angeles. All right then. So let's dive into modern TTS. So let's review the story so far. So let's review the story so far. So in the first week, we've sort of like talked about building sound from scratch. As we went along the weeks, we started talking about different synthesizers. And then in the past few weeks, we've been diving into text-to-speech. We've talked about the concatenative, all of the historical parts. And earlier this week, we've been going into Neuro TTS. And today is the last lecture on modern TTS. So let's review the story so far about Neuro TTS. So back on Wednesday, Anthony talked about two different approaches for doing Neuro TTS. We had the Polynesian approach, where you try to subdivide the problems into smaller chunks, as well as the Portuguese approach, where you simply do everything all at once. Last lecture, Lachman talked about a model called tachytron, which is one of the Polynesian approaches, where you have different stages, one for the phonemizer, the model itself, the vocoder, in order to get the sound that we're trying to generate. Today, we're going to be looking at the Portuguese approach, quote-unquote Portuguese approach, where we simply do everything all at once. And the model that we're going to be looking at is called the VITS model. So here's the agenda for today. First, we're going to look at how do we get to end-to-end models. Then we'll be looking at one particular model, which is the VITS model. And for the last third, we're going to be looking at extending TTS beyond just generating a single voice. So let's dive in, end-to-end models. Now the first question is, why do we even want to do end-to-end models in the first place? So any of you have ever played a game called charades or telephone, where you have like a line of people and and then the person in the front knows sort of the prompt, and you have to pass along the message through some means, either drawing on someone's back, or acting it out, or communicating with some limited means. As you know, as the message goes along, oftentimes the information gets lost or gets corrupted along the way, and that is the main problem with multi-stage models, which is the representation can become the bottleneck of information. And you have to make sure that when you design the representations of each stage, you actually know that it is sufficient for the next stage to be able to interpret it. And what makes things worse is that at each stage, that is not the first one, it has to be able to interpret this kind of compressed or compacted representation that may have some information loss along the way. So for example, in the case of tachytron, the front end might compress stuff into phonemes, but then it converts it into the Mel spectrograms, but there isn't really a guarantee as to like whether or not it is the optimal representation for the next stage to be able to generate the correct audio. So the main approach for end-to-end models is to forget about these intermediate representations. What if we just stack everything together and let the model sort of learn on its own what is the best way to represent the information? Some other main benefits of having end-to-end models is that there's just reduced complexity in terms of management or deployment. For example, if you trained say a tachytron model with a specific front end, what happens if that front end changes? You have to make sure that the twos are compatible, and sometimes things can get complicated as you train more and more models in practice. The other thing is that because you have a single model and they're all in the GPU, you don't have to have all these weird representations that might not be that GPU friendly. It is a lot easier to optimize, and you get better performance from the models of equivalent size. So now that we know the benefits of end-to-end text-to-speech models, let's try thinking about how can we get to these end-to-end models. Now, the actual history of end-to-end model TTS is pretty complicated, as you might see in the diagram from Lachman's lecture. So to simplify things, let's just pretend that end-to-end models does not exist, and the only model you know of is tachytron. How can we try to get from the multi-stage model and sort of turn it into something end-to-end? Okay, so here's a tachytron model. You have the 4 stages, which is the text, the linguistic features, the acoustic features, and the waveforms. And you have the different stages that convert from one representation to the other. We have the front end, which changes stuff into phonemes, tachytron itself, which changes to Mel spectrograms, and the vocoder for the waveform. Before we go any further, let's just change them to slightly more generic terms. Usually we call them the front end, the acoustic model, and the vocoder. Now, let's get into converting this into an end-to-end model. The first step is that in order to get an end-to-end neural network method, everything has to be a neural network, obviously. Now, the main problem is in the front end section, where a lot of times you have methods that are rule-based, such as e-speak or sort of dictionary models, and these things don't really work well in terms of backpropagation or being trained with a neural network. So we just simply replace it with some kind of encoder neural network. A lot of times these neural networks tend to be convolutional neural networks, where you sort of have a sliding window where you calculate on the different features. While the other 2 stages here are already neural networks, so we can kind of leave them as is. The next step is to change from passing intermediate values to passing latent representations, which you can kind of think of as a sort of a very high dimensional vector that encodes the information in some kind of form that the model sort of learns. Now, in order to do this, we know that at each model, since it's trying to go to some kind of latent representation, you have these sort of output layers where you try to collapse all of these latent representations into something that that can be represented, say, as a linguistic feature, for example. So what we do is we just remove them and then simply pass in what is in the output layer to the next model. And now that we do that, we can simply treat these sort of different stages as a single model, since they're just passing in these latent representations, and that backward propagation can be done easily. So here's some notes on end-to-end models, is that a lot of these models are called variational models, as if you look into the literature. The only distinctive feature of variational models is that there is some kind of a probability they're trying to calculate, but it is intractable, so you simply do some kind of approximation. That is a term that you might see. The other part is that even though many of these models are end-to-end and can accept raw text, a lot of times in practice, people still train or deploy them while using some kind of a phonemizer to convert the raw text into something like an IPA or ARPA bit. And it tends to have slightly better results. However, we're just going to ignore that for now and assume that the input is text. because these models are compatible with them. All right then, so now let's go into the next part. This is going to be about a specific model called Variational Inference with Adversarial Learning for End-to-End Text-to-Speech, also known as VITS. Until today, I still have no idea how did they get with that acronyms, but just stick with me for now.
Drop some letters.
Yes, drop some letters. Thank you, Nico.
They call it Burrito-tron.
We have some, yeah, maybe Burrito-tron.
Anything ending in tron.
Okay, so let's hear some examples of how this model compares to the tachytron model from last time. So on the left here, we have the Grace audio, which we use at Gridspace. And on the right, we have LJ Speech, which is a known benchmark that is used for evaluating different text-to-speech models. Please do note that for our use case in Grace, it is meant to be used with a phone, which has a much smaller bandwidth. So if the audio sounds a little bit telephony, that's a reason why. Okay, so let's start with the Grace audio. And the VITS. And now for the LJ Speech.
Anyone with VITS?
Yes. So for the LJ Speech, it might be a bit harder to sort of like tell the difference between the two. But especially for the Grace audio, the VITS model has a much higher fidelity and is much more natural compared to the tachytron. So let's dive into detail. How does the VITS model work? So here is a simplified diagram of the VITS model itself. So this kind of matches with the 3 stages that we have in the previous presentation on tachytron. So over here we have the embeddings, which is sort of like the encoder section of the model itself. We take in the text, pass it through an embedding layer, which converts the raw text into a set of vectors that kind of correlates with the representation of the text, as well as a bunch of convolutional layers. Now, the reason why we want to do convolutional layers is that we want to have some level of context as to what are the surrounding letters. And you have this kind of information as to like what it is trying to pronounce. Then we go through this middle section, which will actually go into a bit more detail in a bit. And this is the part where we map from the text space to the Mel spectrogram space. And we use a type of model called flow models, which we will go into a bit. And the main difference from the VITS model compared to the tachytron model is instead of using an autoregressive decoder, we use something called a duration predictor. And this is a very important part into what I think is why the VITS model works very well. And we'll get into that later. And finally, on this side over here, we have a stage that is very similar to tachytron, which is we pretty much take the hi-fi GAN WaveNet decoder and just slap it on to the middle section. The way we train it is kind of similar, but instead of training stuff in steps, we simply feed the model and train them back to back. So now let's get into what I think is the most important contribution of the VITS model, which is the duration prediction. This is sort of like the central piece over here. Now, the main problem that the VITS model that this duration predictor is trying to solve is the problem of how do we map representations from the text side to something that is a representation on the audio side, which is also introduced as the sequence-to-sequence problem during Anthony's lecture. So we have a bunch of text over here, and usually it's not that much. For example, if it's the word hello, it might be just like 6 letters. But on the other side, we have the decoder, which is expecting things to be in the sort of like frames or like short snippets of sound. And the problem is, how do we match them such that not only are they monotonic, meaning that you don't get weird mappings that sort of like have a cross like this, for example, like in order to preserve its temporal qualities, but also so that we don't accidentally drop a bunch of letters and have like missing sounds in our generated audio. Now, the way Tachytron sort of solved this problem is using an autoregressive decoder. As Lokman introduced in the last lecture, we simply pass it through a bunch of layers in order to get some kind of representation. And then we sort of continually generate section by section according to how long each section is supposed to be. Now, the problem with using an autoregressive decoder is that all of the later steps are dependent on the outputs of the first steps. So it means that we can't really parallelize this process. And because we keep feeding its output over and over, it can become unstable over time, which means that if you have longer sequences, the quality of the audio might degrade over time. Now, in order to combat this, the VITS models uses a method that was inspired by a paper called GLOW TTS in 2020. And this uses this kind of method here called a duration predictor. The way this works is it looks at the input, the representations of each token, and then it passes through a model. This model predicts a single number, floating point number, that sort of says how many frames does this token supposed to be. So for example, if you have a longer vowel, for example, if you're supposed to say hello, the remaining O can be mapped to multiple frames. Whereas shorter sounds, such as like if you have some kind of like a stop consonant, it can be mapped to fewer. Now, once we predict these values over here, we simply round them up to the nearest integer. And the reason why we need to round up to the nearest integer is so that we can simply do copies of these representations. And once we do the copying, we now have a sequence of encodings that matches with the temporal data that the decoder model is expecting. Any questions so far? Now, the main benefit of doing this is that not only is this process very parallelizable, because these representations over here isn't really dependent on, say, this representation over here. And having a simple model that is pretty much a bunch of convolution layers is pretty quick to compute. So you have much lower latency compared to autoregressive models. And since we're simply duplicating the outputs and we're not sort of doing these kind of like feeding loops, we also don't get the instability problem that happens with autoregressive models. But there's a catch to this particular approach in GLOW TTS. And that is, because we're predicting the numbers directly, the model is deterministic, which means that if you input the same text, you would always get the same timing. And that is a problem because in order to create a natural sounding speech, you want to have some variations, even though the person is saying the exact same sentence. To combat this, the VITS model, which was invented in 2021, uses a different approach, which is called stochastic duration prediction. Now, instead of calculating a single number, the stochastic duration prediction algorithm predicts a distribution. So the way it works is you take in some kind of Gaussian noise, and then you pass it through something called a flow model, which converts this simple Gaussian noise into a more complex distribution that represents what is the distribution of timings for each token. Then from here, you can just simply sample. You can just sample how long that token should be, and be able to get its timings. So with this approach, each time you generate, because you're sampling, you simply get a different number. And because of that, you can get varied speech. All right then, are there any questions so far? So in this part, I'm going to take a short detour into some other methods that are used in TTS. One of the methods which was introduced in the paper Natural Speech in 2024 is what is called a phoneme encoding pre-training. So at the first stage, normally you would train a stage of neural networks with the entire model. However, one way that you can improve the efficiency of this model is to do a BERT-style pre-training, which is you take like a series of phonemes, you mask out some of them, and then train the model to sort of like fill in the gaps as to what is missing. And the hope of this approach is such that the encoder, which is like the first stage, can learn the relations between different input phonemes and hopefully have a better result. The other approach that it is used, but not in the VITS model, is diffusion. Now, in the VITS model, we use a method called flow models, which is you have a bunch of invertible functions that kind of iteratively convert a simple distribution into something more complex. Diffusion is similar. However, the main difference is that the diffusion process is not limited to invertible functions. It makes it more expressive, but it also means that when you try to run it, you always have to run them sequentially, and a lot of times the latency is a bit higher with diffusion models. So now we're on to the last third of our lecture. Now let's think about what can we do with TTS if we're not limited to just simple text inputs. What if, in addition to just the text inputs, we also have side inputs? And there are a few ways that you can do this. The first idea is, what happens if we want to have multiple speakers? One way that you can do a side input is to simply have different speaker IDs. So during training or inference, you give it an ID, which goes through an embedding, and then you pass this information into all the layers. And this was done in the VITS model, so that a single model can generate multiple voices. Kevin, could you help me play this, please? Thank you. So here's the first voice.
Holy shit.
And here's second.
No.
As you can see, a single model can produce very wildly different sounds. The second idea is, what happens if we embed something a bit more complex? Say we have a text prompt. And the way it works is similar, is you have a text prompt, and then you put it through a language encoder model, and then take the resulting representation as a context to input in addition to the text that you want to generate. For example, in prompt TTS, this model uses a BERT encoder, where in addition to the text, you can simply tell it what kind of voice do you want to say. For example, here, you prompted, okay, the man says sadly, and here's the generation result. And here's the exact same text, but you say, the man shouts. As you can see, we now are able to influence how the voice is generated so that you can get more varied and fine-tuned response. For this last idea, what about if our input isn't a text, but actually a voice clip? This is also known as few-shot voice cloning, where you have a text you want to say, you have a reference clip, and then you try to generate a sound that is similar to the reference clip, but says the things that you put in the model. Oops. Yeah. I think this thing's jammed.
We're gonna do some All right. Well, got any jokes?
No, not really.
This thing sucks.
While we're waiting, if we're unable to resolve this, you just have to take my word for it. The paper is from natural speech. Oh, okay. So all right then. Here is the reference clip. And along with this text input, which is inserted during the generation process, here is the output. All right, then. So that's the content I have for our last lecture on TTS. This is a quick overview of how modern TTS works and how you can extend it further from just text. Any questions so far? Yes?
So as somebody who has implemented this, what are some of the practical challenges?
Okay, so the question is, as someone who has implemented TTS, what are some of the practical challenges? So for me, I think one of the biggest challenge, especially with the newer models, is getting data that has very high quality. One of the problems that we encountered was that some of our data, for example, had like a slightly longer pause than usual. And with the previous models, because it wasn't as sensitive, it didn't really pick up on that. But as you get to better and better models, those like ending trailing stuff can sometimes mess with the duration predictor, and then you would get some kind of hallucinations at the end of the text. So like you say, hello, my name is Grace, and then you hear da 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 at the end. Another way that this can kind of mess you up is that any kind of sort of like quirks or sort of like mispronunciations in your data can manifest itself in like the final generation. For example, sometimes the voice actor, because she was saying quickly, the word to kind of sort of devolved into tuh, and then we get this kind of generation where the word to becomes t, even though we did not intend for that. Yes?
Do we train with 8K audio as the output, or do we downsample to 8K?
So the question is, do we train on 8K or do we downsample to 8K? So the answer is we train in 8K. Actually, both approaches are valid. The only reason why we prefer training on 8K is that the difference between the models is not that much. And by training at a higher frequency, you're simply using a lot more compute than if you trained an 8K model. So a lot of times if you're in, say, an application such as like going through telephones like Gridspace does, you do have to, it is advisable that you shrink down the model to accommodate for the actual quality that you're looking for. Any questions from online? Or from here? Yes?
Does the hi-fi GAN still use the discriminator and generator?
The question is, does the hi-fi GAN still use the discriminator and generator? Yes. There's in fact multiple discriminators and generators in the VITS model. There's some for the generator, there's one for the duration predictor. There's actually a picture by Lokman that sort of like shows how all the gradients sort of flow. I did not put it in my slide deck, and it's pretty complicated, to say the least. All right then. Anthony, do you have any closing thoughts for the course?
Sure.
All right then, that's it for me.
Am I supposed to do magnet? You want to stay up here, actually? Another round of applause for Nick. What an incredible end to the series. Well, a couple things. One, just what an awesome series. This is the third year we've done this. This is by far the best one we've ever done. You watch the old ones, but they're not as good as this. We started with like sine waves and white noise, and we ended with real-time, flawless reproductions of human speech. So what a cool journey. I wanted to thank our guests and partners, so AILA, Chris and Steven from Noise Engineering. It was awesome having them. Ange Yaghi on physical modeling. It was amazing to have him. Obviously, John Chowning, the inventor of FM synthesis, like it was a true honor to have him as well. We wanted to also, again, thank Sandy Disner from USC and Gene France from TI, pioneers in speech synthesis. And then I wanted to thank, where's Natalie? Yeah, Natalie, come up, come on. So Natalie did an amazing job putting together this series for us. So again, another round of applause. Natalie asked me to say that, so if you liked these lectures and you're like, man, boy, would I like to do this for a summer or forever. Boy, do I have news for you. You can email us at hiring@gridspace.com. Also, Phoebe, do you want to come up here? We're going to talk more. She didn't really do it. Phoebe and I are going to be at MIT next week. If you're watching this in the future, we were at MIT at one point. So if you're interested in full-time positions or internships, or you just want to talk more about IAP in person, we'll be at X-Fair and we'll be on campus all of next week. Additionally, Nick, if you liked his lecture, he also is running the internship program this year. So if you're interested in an internship at Gridspace, reach out to us as well. You can go to iap.gridspace.com/internship, I think, is that right? Yeah, and we'll post it in the thing. And we've had other past IAP participants join as interns, and we've had a lot of interns join the company. So I think that's it. Again, round of applause for Natalie. And again, Nick, great way to finish it off. So incredible. All right, well, that's it. Thanks, guys.